Hello and welcome to another video lecture. This is week 3, topic 2. We are going to talk about transform boundaries. We can see right here in the middle the most famous transform boundary in the world, the San Andreas Fault. So let's talk about how these things work and what the different kinds of faults are. Just to recap, stress is a force applied over a given area, and there's 3 main kinds: tension, compression, and shear. Strain is the way an object deforms as a result of stress being applied. This first cube is being stretched because tensile force is being applied to it. The second cube is being compressed because a compressive force is being applied to it. And this last one is being sheared. It's being deformed in this manner because of the rotational stress being applied to it. And there's 3 main kinds of strain: brittle, elastic, and plastic. And we'll come back to these. In laboratory experiments on rocks, we can see that they deform elastically under slight strain, then plastically with a little bit more strain, but ultimately they will break because rocks are brittle objects. Under a little bit of strain, we can see the sides starting to bulge out, and that increases with more and more strain being applied to it. And then ultimately some cracks start to form as we pass that failure point, as you can see on the chart down below, and enter an area of brittle deformation, where we are getting cracks and breakage of the rock in addition to the surrounding plastic bending deformation. We get plastic deformation in between the yield point and the failure point of your object, and elastic deformation between the start of your stress and strain application to that yield point. There's an important thing that faults do. Fault is any fracture in the rock along which motion can occur. And in the crust, faults move over time. While some faults do move continuously all the time, usually what we get is called stick-slip behavior. Now let's just watch this video and get a fix for what stick-slip behavior is. So this video shows a block of sandstone rock sitting above a block of granite rock, and it's being pulled at a continuous rate by this hook on a string. The hook on the string is connected to the block of rock with a spring, so we are building elastic tension in that spring, and then you can see it is starting to pull the block of sandstone. But it's not moving continuously, it's kind of lurching, and this is what rocks do in the crust. Most faults move like this. It's called stick-slip behavior. It sits still until enough elastic force builds up, and then it overcomes the frictional force of the contact between the rocks, and it slips. And that slippage is an earthquake. An earthquake is a battle between tectonic loading, represented by the hook on the string, the elastic force of the crust, and the friction between your 2 sides of your fault. And we can see from the chart, which records the shear and normal stress and the time, that it's not always the same. It varies a little bit just because of inconsistencies in the rock, variances in your frictional force, and all sorts of minute details. In the Earth's crust, this manifests as something called elastic rebound. Down here we can see an old picture of the San Andreas Fault shortly after the 1906 San Francisco earthquake that heavily damaged the city, and this fence has been offset along the San Andreas Fault because after the earthquake the fault moved. We can see that this fence used to be straight. It has been offset at the fault, but it's also a little bit wavy. It's not perfectly straight next to the fault, because as that tectonic loading elastically deformed the uppermost crusts of the rock, that fence was bent a little bit. And then once that elastic force was overcome, the frictional force was overcome by the elastic force, and the fault ruptured in an earthquake. We call that rupture, and that offset the fence as well as re-deforming the sides of the fence. We can see in this sort of 3-panel comic here the way that worked. So take a second to look at that. When these faults break as a result of the elasticity overcoming the frictional contact, that's an earthquake. An earthquake occurs when stored energy is released suddenly. It's also when a section of the Earth's crust breaks along a fracture called a fault. One side of the fault has to move relative to the other side of the fault. That is what an earthquake is and has to be. This releases energy, which produces vibrations of the ground known as seismic waves, which move away, they radiate out from the point of rupture, which is the hypocenter. That's our new featured word for this lecture, is hypocenter. That is the actual point at which the earthquake begins, deep underground. The epicenter, which is probably the word you're more familiar with, is the point on the ground surface directly above the hypocenter. But remember, a fault is a large planar area. It's a weak plane within the crust. It's not a single point. So these earthquakes actually rupture an area of that fault plane. But let's talk about seismic waves for a second. Seismic waves, those ground vibrations released during the earthquake, move away from the hypocenter as different types of motions. There are 4 different types of seismic waves. 2 types of these vibrations travel through the Earth and are called body waves, and 2 types of these vibrations travel only along the surface and are called surface waves. So body waves are the ones that radiate through the Earth's interior, and surface waves only travel along the ground's surface. You remember from Lecture 1, we discussed that body waves from earthquakes can't travel through liquid, so they do not pass through the Earth's outer core. Surface waves, however, do reach all parts of the Earth because they travel all the way around the Earth's circumference. You can also picture this by hitting a plate on the ground with a big hammer. Then we get these surface vibrations, which you can feel, but there are also body waves, which you can't feel as much, that travel radiating in all directions deeper into the subsurface. These are the 4 different types of seismic waves. P waves, or primary waves, are a body wave that manifest as expansions and contractions very minute within the medium, or I guess rock if you're talking about the Earth, that the seismic waves are traveling through. The second kind of seismic wave is called an S wave, or a surface wave. These are actual vibrations, movements of the ground surface, where it moves up and down. These are generally the most damaging kind of seismic waves. There are 2 other kinds, Rayleigh waves, which move in a rotational manner, more like ocean waves, and love waves, which are body waves that move as lateral vibrations within the rock. The love waves and Rayleigh waves are less common. They don't travel as far from the earthquakes, but the S waves and P waves can usually be recorded on the seismometers around the entire globe during an earthquake. To see what these ground motions look like during a major earthquake, please pause this and watch the additional 2 videos on motion during an earthquake, which are linked on the D2L page. Now, back to faults and their geometry. To discuss faults, we need to talk about something called strike and dip, which is how we, as geologists, describe the orientation of geologic features. The strike is the direction of a line made by the intersection of your tilted layer of rock or a fault and a horizontal plane. The strike is the direction your body is oriented. We can see in this 3-dimensional model up on top. These tilted blocks of rock have a strike, which is a directional orientation, and a dip, which is the angular difference from horizontal. The dip, again, is the angle between horizontal and the top of a tilted layer or fault plane. That has a number in degrees and a direction. So, for example, on this lower one, it is dipping 20 degrees to the southwest, as shown by this map symbol here. Take a second to look at these diagrams and understand what the strike and dip is. Because a fault is a planar fracture, we can talk about fault planes. In this diagram below, the fault plane is shown in red. Usually this is a tilted planar fracture that extends through a significant portion of the Earth's crust. Again, the strike is defined as the compass direction the fault is pointing of the line that is created when the fault plane intersects the flat surface, like the ground. But the fault's dip is defined as the angle of the fault plane relative to a horizontal surface, also sometimes the ground surface. In a fault, we talk about the hanging wall and the footwall. The hanging wall is all the material above a tilted fault plane, and the footwall is all the material that is below the fault plane. If you can imagine yourself in a tunnel intersecting that fault plane, you are standing on the footwall because it's below the fault plane, and the hanging wall is above you, where you might hang your lantern if you're in that tunnel. So again, hanging wall, the material above the fault, the footwall, the material below the fault. Broad-scale tectonic forces of tension and compression cause movement along the dip of the fault plane. The hanging wall will move up or down relative to the footwall. Shear stress, however, causes motion along the strike of the fault plane. So when we look at this simple block model here and the types of stress causing that deformation, tension causes the hanging wall to move down relative to the footwall. A compressional stress does the opposite, and the hanging wall will move up relative to the footwall. A shear stress usually prefers to have a vertical fault plane orientation and gives you lateral movement along your fault. That fault motion, again, can occur along the dip, the strike, or both. So when we have just vertical motion along a tilted fault plane, we call that dip slip. Lateral motion along a vertical fault plane is called strike slip, thus the name strike slip fault, because your motion is occurring along the strike, the orientation of your fault. When you have both of these at the same time, you get oblique slip, so your fault plane is moving diagonally. The hanging wall moves diagonally relative to the footwall. Most major faults have some oblique component to them. So let's talk about what we call normal faults, where the hanging wall moves down relative to the footwall. This occurs when you have a tension stress. This causes the hanging wall to drop relative to the footwall. The section of land along the fault widens but also thins, and that's important. This is called a normal fault. The dominant stress is normal, or parallel to gravity, and that's a physics term. The normal stress is also synonymous with gravity on Earth in most conditions. A very low angle, so very shallowly dipping normal fault, is called a detachment, and we'll talk about detachments when we get to Death Valley National Park. You can see that in this lower half of the diagram, where we have a very low angle normal fault accommodating a huge amount of dip slip, and that causes a huge amount of folding and also a scoop or spoon shape to this fault surface. We find these kinds of faults at divergent continental boundaries and areas of continental rifting or thinning, such as the Western North American Basin and Range. And I'll talk about that right now. Where we have areas of crustal thinning or spreading, we get what's called Horst and Graben topography. So that's a series of normal faults that are accommodating a broad-scale tension in the crust. Above on the right here, we have one single normal fault. We can see the offset in this layer of rock where there has been, probably 5 feet of vertical motion along the dip of this fault. On the left, we have an area of Canyonlands National Park called the Grabens, where there has been some crustal upwarping, so it's been thinned because it's been stretched as the land rose a little bit. And as that happened, that created tension in this overlying layer of sandstone. So we have these faults bounding areas called grabens, which is a basin bounded on 2 sides by normal faults, and a horst, which is a risen or uplifted area between grabens, also surrounded by normal faults. These grabens, or structural valleys, are created when a block of crust, the hanging wall, drops along 2 normal faults. The footwalls of the faults remain high and are called horsts. So when we talk about an area of North America called the Basin and Range Province, which constitutes a portion of eastern California, almost all of Nevada, southeast Oregon, parts of Idaho, and about the west half of Utah, and then a little further south, the south half of Arizona, portions of New Mexico, and northern Mexico as well, The Basin and Range Province is an area where we have series of mountain ranges, or horsts, separated by valleys, or grabens. So we get valley, mountains, valley, mountains, valley, mountains, horsts and grabens all the way across the Basin and Range Province. That is because this region of North America has been stretched as much as 20 to 30% in some places relative to its original position. Here's another view showing the national parks associated with the Basin and Range. The largest one, Death Valley National Park, will get its own due time when we're ready for it. There's also a Great Basin National Park, which occupies the horst, or mountain range, of the Snake Range, one of the more dramatic ranges in Nevada. Very scenic, very cool. But this topographic relief map shows the mountains and valleys a bit more clearly than that previous map did. Now we're going to move on to what happens when you get compression. This causes the hanging wall to rise relative to the footwall, so it's the opposite of a normal fault. The section of land along the fault narrows and also thickens. This type of fault is called a reverse fault. A low-angle reverse fault, that should be reverse fault right there, is called a thrust fault. You find these at convergent plate boundaries and areas of crustal shortening. So in these block models below, you can see the compression force is causing this rather steeply inclined fault, the hanging wall to rise, and the footwall to sink down. When you get a low-angle reverse fault, the land will be pushed up and over and fold as a result of it. And this is called a thrust fault. And this is where you get areas of crustal folding. These rocks are actually folding. They are bending rather than fracturing. Some fracturing occurs during the process, but by and large, the rocks actually bend under their own weight rather than break. This is a small reverse fault in Titus Canyon in Death Valley National Park. You can see this white rock layer has been offset by a fault plane that runs somewhere along in the middle here. Take a second to look at it and see if you can find the fault surface, and then I will draw it in. Okay, and here's the fault surface. The hanging wall, the upper portion of the fault, has moved up relative to the footwall as a result of shortening of this block of rock. Compression has pushed the upper part, the hanging wall, over the footwall. Finally, we're going to talk about shear stress, or transform boundaries. Transform boundaries can connect other types of plate boundaries. Depending on the configuration, the transform boundary may grow, shrink, or remain constant. In western North America, the San Andreas Fault, which is our major transform plate boundary between the Pacific Plate and North American Plate, is dominated by shear stress, a rotational stress. So we have near vertical fault planes and strike-slip faults. The San Andreas Fault connects the divergent spreading centers of the Sea of Cortez, or the Gulf of California, and the spreading center between the Cocos Plate at the south and the Pacific Plate, where we have sort of northwest to southeast oriented spreading. The San Andreas Fault links these spreading centers with the spreading center and subduction zone found around the Juan de Fuca Plate off the northwest coast of the United States, rather. Shear stress causes motion along the strike, and we can see a vertically oriented point wants to rotate between these laterally sliding blocks. The hanging wall does not move up or down relative to the footwall in a pure strike-slip fault. Because your lateral motion is concentrated along the strike or orientation of the fault, it's called a strike-slip fault. Strike-slip faults are either left lateral or right lateral, depending on the relative sense of motion. So if you're standing on one side of the fault, it depends on what the other side of the fault is doing. If you're standing still on this side of the fault, this version of the fault on top here is moving to the left, and that makes it a left lateral fault. Now the opposite, if you're standing on one side of the fault and the opposite side of the fault is moving to the right, that's called a right lateral fault. In these two images here, we see two strike-slip fault zones. Up above here, we have a left lateral fault zone where the far side of the fault is moving to the left relative to the near side of the fault where the camera is standing. Rather than being one single fault plane where all of the motion is concentrated, we have a series of parallel strike-slip faults that, over the width of this fault zone, accumulates a couple feet of lateral displacement. Down below, we see a right lateral fault, where the distant side of the fault is moving to the right relative to the near side of the fault where the camera is standing, as marked by these resistant beds of rock. Higher up in the crust, fault zones are very brittle, so we get broken rock, and in that you get a fault breccia. This one is from Death Valley. You can see the fault surface making a nice, sharp, clean vertical surface here, and these fragments of broken rock right along the other side of the fault. The camera, this is a normal fault, and I'm standing on the hanging wall, and this is the footwall that's been exposed by motion along this fault, exposing these chunks of rock, or clasts, suspended in sort of a clay, silt, sand matrix. This is called a fault breccia. The other thing you can get is pulverized rock, or clay-sized particles, and that's called a fault gouge. In this picture down below, I'm not sure where this is from, you can see a zone of fault gouge on sort of in between. You can see this zone of fault gouge where repeated motion along this fault has completely pulverized the host rock and turned it into clay and silt, very small-sized particles. Lower down in the crust, the fault zone is actually slightly plastic, and under enough pressure you get a new type of rock created, and we call that a myelinite, which is a low-grade metamorphic rock with smeared out, sort of plastically deformed mineral grains. When you look at these two examples, we can see that they look smeared and sheared and broken up laterally by high-pressure motion along a fault zone. This one down below shows these quartz clasts that have been smeared and stretched out and deformed by high-pressure motion along this fault zone. So instead of rock breaking in a fault, you get this zone of plastic deformation. This has to occur deep in the crust, so this rock has been uplifted a fair distance to be visible at the surface. So let's go back to the San Andreas Fault. It is a transform plate boundary. This is how the San Andreas Fault has evolved over time. About 30 million years ago and earlier to that, we didn't have the Pacific Plate off the west coast of North America. We had a different oceanic plate called the Farallon Plate, and it formed a huge subduction zone that stretched from Alaska all the way down through Central America down to South America, where it met up with the Cocos Plate, which is still there. The Farallon Plate has almost completely subducted, and when it did, then we had Pacific Plate in contact with the North American Plate. But the Pacific Plate is moving a different direction than the Farallon Plate was. It's moving to the northwest. And so because the Pacific Plate is now in contact with the North American Plate, that makes a sliding boundary, or a transform boundary between the two plates. As the Farallon Plate continued to subduct and split into the Cocos Plate and the Juan de Fuca Plate, that transform boundary expanded and became much, much longer. Over time, that transform boundary transformed into a divergent boundary along the Gulf of California, between Baja California and mainland Mexico, and it maintained itself as a transform boundary north of there through California until it meets up with the Juan de Fuca Plate. This is an animation showing that very process that I hope will make it a little clearer about what happened. So we have subduction of the Farallon Plate. It eventually, ultimately, completely subducts beneath North America, and we get a new transform boundary forming. Some really complicated tectonics happen in Southern California, and as that transform boundary matures and grows, we get stretching of the crust, creating the basin and range in Nevada, Utah, Arizona, and Eastern California, and then we get the modern-day San Andreas Fault, which has been in place for about 20 million years. Let's watch it again. So about 30 million years ago, the Farallon Plate subducts, and we get the initiation of a transform boundary about 20 million years ago, Complicated stuff happens in Southern California. Then about 10 million years ago, we get a modern San Andreas as we know it today. The last 5 million years, it maintained its current geometry. And then over the last 1 million years or so, it looks exactly as it does today, with some, again, very complicated tectonics going on in Southern California. This plate boundary, again, links the subduction zone and spreading centers of the Juan de Fuca plate at a triple junction with the spreading centers and divergent boundaries in the Gulf of California. The San Andreas fault system is famous for its capacity to generate large earthquakes. Its last major earthquake occurred in 1906 and stretched from the city of San Juan Bautista in central California all the way up to the boundary with the Juan de Fuca plate and the Cascadia subduction zone. That was a very large earthquake, probably a magnitude 7.7 or 7.8. Prior to that, the southern San Andreas, so the San Andreas Fault has three main sections: the northern San Andreas, the central San Andreas, and the southern San Andreas. The southern San Andreas Fault last had an earthquake in 1857, and it was a very large earthquake as well. We don't really know how large that one was. But the central section of the San Andreas Fault actually moves continuously. That's called the creeping section. So it moves continuously because the rocks that form the San Andreas Fault are very slippery. These are rocks called serpentine, which is made of very slippery, very planar kinds of minerals that prevent large amounts of friction from being built up. It can still rupture as an earthquake, and earthquakes have been recorded in the creeping section, but generally it moves continuously more often than it moves in large earthquakes. That leads us nicely into Pinnacles National Park, which borders on the San Andreas Fault on its northeast side. Pinnacles is in the central coast of California in a mountain range called the Gabilan Range, and it protects an area of very scenic rock outcrops. It's named for these striking rock towers and cliffs that are all composed of 22 to 23 million-year-old rhyolitic volcanic rocks, and most of these are pyroclastics and breccias. This national park is one of our most recent national parks. It was established in 2013, upgrading a national monument that was established in 1908 for the area's scenic beauty. But the geologically interesting part about Pinnacles National Park, and the reason it was upgraded from a national monument, is that this only represents half of the rhyolitic volcanic complex. The other half of this rhyolitic volcanic complex is 195 miles away to the southeast in the Mojave Desert. So we can see in this map of California the San Andreas Fault as this red line. It's a right lateral fault, which means the west side of the fault moves to the northwest and the east side of the fault moves to the southeast, relatively to the right. And this San Andreas Fault has split a rhyolitic volcanic complex. Pinnacles is the national park today, which has towering rock pinnacles and high relief topography. But the Nenach Volcanics, which is the other half of the volcanic complex, is made of relatively low relief hills. And it looks pretty much like this. This is part of the Mojave Desert, or very near the Mojave Desert, and its southern edge is defined by the San Andreas Fault, whereas the Pinnacles area, the northwest part of the park's rhyolitic rocks, are defined by the San Andreas Fault. These rocks share the same exact age and the same exact chemistry, proving that they were once connected and that there has been 195 miles of movement on the San Andreas Fault in the last 22 to 23 million years. And that is pretty incredible. Now, please take a minute to watch the summary video on earthquakes and plate tectonics, and I'll see you next week.